Hi everyone, this is Mrs. Cooper,
And this is Mrs. Backus.
and this is our video on how to measure liquids using a graduated cylinder.
You've looked at graduated cylinders already in your lab drawers, and they look like this picture here. Laboratory equipment that's used to measure the volume of liquids. And you can have small and big ones, and they usually range from about down to little tiny ones, 5 milliliters, or up to something big like 2,000 milliliters.
I think you can have larger ones, but here in our lab, the largest one we have is 2,000 milliliters.
That's
right?
correct, yeah.
Okay. So when are we supposed to use a graduated cylinder? If we see here, we have different pictures of lab equipment, and we see that as we move to the right, the precision and accuracy increases. So when you're measuring liquids using a flask or a beaker, like the ones on the left, the precision and accuracy is not that good.
Yeah, I've seen people do that.
Yeah.
And I know that for beakers and flasks, they don't really represent the actual milliliters. It's kind of a approximation. And so that's really bad to use those.
Yes, exactly. And when you are trying to replicate an experiment, you might have trouble with your replication if you were not precise and accurate with your measurements from the beginning. And we see there on the right that we have a pipette and a volumetric flask, and these are better than a graduated cylinder if you really want to be accurate and precise.
So we've been using these terms, precision and accuracy, which you already looked up, but in case you forgot, I just remind you that precision is how close the measured values, so if you do many trials, you have multiple values, how close they are to each other. Accuracy, on the other hand, is how close a measurement or the average of your measurements is to the actual or accepted value. And when you have both, the values are close to each other and to the actual value. So you can see from this picture right here, it's a target, and these marks on the target are close to each other, but what's wrong with them, Ms. Cooper?
I don't see they're right in the center.
They're not in the center. Now these, the average gives me about the center, right?
Yes.
So the accuracy is good, but they're not that close to each other.
No, they're not. What about the ones in the middle?
Yeah, the one here, they're not only close to each other, but they're also in the middle. So this is precision and accuracy.
Very good. So when you're measuring the liquid in a graduated cylinder, you might have noticed that the liquid starts to kind of like stick to the edges. So this is because surface tension, and this that looks like a belly, it's called the meniscus. It's not like the one you have on your knees. It's a different meniscus, the one we use in chemistry. And we have a picture here with two different liquids. So the one on the left, it's a solution based in water, and here on the right we have mercury, and you see they have different shapes. So when you're reading the meniscus, make sure you read the bottom. Usually we will be working with this kind of meniscus, the one that has the kind of like the belly on the bottom.
Because they don't let us play with mercury anymore.
Exactly, it's very toxic. So we will be using most of the times liquids or solutions that have a meniscus like letter A, and make sure that you read the bottom part of it.
But if you did measure mercury, which you won't be doing in this class, you would read the top of the curve instead of the bottom.
It's different. Yeah.
How do you go about reading a graduated cylinder? Well, it's very important to bend over and get at the eye level. And this picture kind of shows what would happen. If I'm below and this picture, if I'm below and I look this way, I might end up with a value that was wrong because it's really too low. If I'm above the value, I might read it as the value is too high. So I need to really look at it right eye level.
So you have to bend your knees and kind of like get your eyesight straight into that bottom part of the meniscus, so you have an accurate and precise measurement.
And this person is also putting a card behind it. Sometimes I like to take a marker and draw a straight line with a ruler and put that up behind. Sometimes that helps me. I've got kind of old eyes now, so
yes.
It helps me see it a little bit better.
Well, even with young eyes, you still need some help sometimes.
Sometimes, yes.
Okay, so when we're measuring, there is some uncertainty. So this can be because of the equipment we're using, or the skills of the operator, in this case ourselves. So here we have an example. We see a picture on the right with it's a liquid in a graduated cylinder, and we see the graduates. These are the ones that have the lines that have numbers. So we have number 10 and 20, and these are milliliters. And between these, we have subgraduates, so the lines that don't have numbers in them. This measurement, if we see here, it's 10, 15, 16, 17. However, there is some uncertainty. How am I sure that this is the correct number? So what I would do here is these intervals are 1 milliliter each, and this 1 milliliter will be divided by 5. We use 5 all the time. That will be our number for measuring uncertainty, for calculating it. And the answer will be plus minus 0.2. So next week we will be talking about significant figures, but we see here already that this 0.2 is a significant figure on the right side of the decimal point. So we need our 17 has to be 17.0 plus minus 0.2 milliliters.
So that 0.2 milliliters means that I can estimate between those lines. So if something is between lines, I don't have to call it right on the line. I can estimate between those lines.
Exactly, yes.
And I think I can estimate somewhere plus or minus 0.2. That's what it's saying. So yes. If you read it and I read it, our two values might not be the same, but they should be within a 0.2 milliliters of each other.
Exactly. So the range will be between 16.98 and 17.2.
Right.
Yeah.
So those would be good answer.
16.8.
16.8.
Yes.
Very
16.8,
good.
yeah.
And the other thing you note, if the plus or minus value is in the tenths place, you have to read it to the tenths place, even if you have to add a 0.0.
Exactly. So the one on there on the left would be wrong. 17 is not the correct answer. It should be 17.0.
All right, let's take a look at that a little bit more carefully. And don't forget to pause the video and write some of this stuff down. So how did we get that plus or minus 0.2 again? So I'm going to talk about that a little bit more. All right, so where did that plus or minus value come from? Well, we have to know what the graduates are. So those are the big lines with the numbers. So we have a value of 10 and a value of 20. So the difference between 20 and 10 is 10 milliliters. So between these two big lines is 10 milliliters. There are 10 little lines between these two big lines. And so 10 milliliters divided by 10 tells me that each one of these is 1 milliliter. And you probably could have figured that out on your own.
You can
probably.
Count.
You can count and say that's 10, 11, 12, 13. But if you wanted to know how we got it, that's one way to get it. So the uncertainty is not 1 milliliter because I can estimate between those lines. So the uncertainty is the smallest increment, which is 1 milliliter, but we still have to go further. We got to divide that number by 5, and then it gives me a plus or minus value of 0.2. So basically I'm saying I can read somewhere between the lines, and the two of us, when we read it, should be within plus or minus 0.2 of each other.
0.2 milliliters. Ms. Backus, I've noticed in some books that they don't divide by 5, they divide by other numbers. Why is that? Is that correct?
Yeah, there's some disagreement in the science community on this, so that's a very good question. We are going to divide by 5. Some people say you can only divide by 2, so they would say if this is 1 milliliter, you would say plus or minus 0.5. Some people even go further than we go and say you can estimate and divide that by 10.
Wow.
So they would say you can have plus or minus 0.1 milliliters. So we're kind of take the in-between route. Instead of dividing by 10, I don't think you can be that good.
No, I don't think so.
And then instead of dividing by 2, I think you can be better than that.
Yes. So 5 is a good number.
So 5 is a good number. But if you take further chemistry classes in college, you might want to check with what they use as their division, because there's debates about what number to use.
Okay. So for this class, we're using number 5.
We're using number 5.
Okay, here's a final example. Here we have a picture of a graduated cylinder. We see that the graduates are 6 and 8 milliliters. And in this case, our subgraduates have, these are intervals of 0.2 milliliters. So when we're reading this, you see we have here a dashed line. It's about 6.246, but the bottom is actually above the subgraduate. So we estimated it was 6.63. Now this last digit is uncertain. That's why we need our plus minus, right?
Right.
So for our uncertainty, we take our smallest interval, which is 0.2, and we divide that by 5, which gives us 0.04 milliliters. So our significant figures in this case, you see we have 2 decimal places after the decimal point, because we have 0.04. The 3 is our estimated digit. What happens if we have an extra 0 here? Is that correct?
No, that kind of implies that I can read this to plus or minus something in the thousandth place. Wow, there's no way I can...
You need like a microscope.
I don't know. That would be crazy to read that. There's no way I can read it that carefully. So if I can only read it to the hundredths place, 0.04 is in the hundredths place, I should only put a number to the hundredths place.
Okay.
And I shouldn't put too many.
No, because you cannot read that.
No,
right?
And I shouldn't put too few, because then I'm not indicating how good my graduated cylinder is.
Exactly.
So I have to read it exactly. And just because it's plus or minus 0.04, I don't have to read that as 6.64, do I, Mrs. Cooper?
No, not at all. So you can have any number here. The one that you estimate is the closest to, it's more accurate. But for example, if you have 0.04 for your certainty, that doesn't mean that you have to count by fours. You can have a 3 or a 5 or something else.
Right. But if both of us read this graduated cylinder, maybe if you look at this graph, the picture of the graduated cylinder, you might say, I don't think it's 6.63. I think it's 6.65. Or you might say it's 6.62. But those are all okay because we're still within plus or minus 0.04 of each other.
Exactly. So we're still in that range.
So basically it's telling you what range is an acceptable value.
Yes.
All right. Well, I think that's covered it.
Yeah, so we'll see you in class. And remember, you should have taken notes on this video. So if you didn't, go back to the beginning and take out a piece of paper and write your notes.
Excellent. We'll see you in class. Hope you enjoyed the video.